Let's look at the electric generator. So here we have a coil that is rotating in a magnetic field. So we are going to actually need to do some mechanical work here to rotate this coil. And the coil is rotating about this axis, and it's rotating in a magnetic field that's oriented in this direction. Now the coil is made of metal, so as it's rotating with velocity that's tangential on these portions of the coil, then all of the charges inside the metal will get influenced by the fact that they're moving with a velocity v in a magnetic field B. So the force that they're experiencing, the magnitude of the force that each of these charges is experiencing, is given by the charge times the magnitude of the velocity, magnitude of the magnetic field, and sine of the angle between the velocity and the magnetic field. Now, since this thing is rotating, that means that the theta will also change constantly. So when we try to find the direction of the force, we have to apply the right-hand rule, place our hand in the direction of velocity, bend fingers in the direction of the magnetic field, and the thumb will go in this direction. And then for the other side of the loop, we would have the velocity going in that direction, magnetic field to the right, and the force will be down. So we would have these positive charges going down here, positive charges going up in that direction. And if we looked at the top portion, what happens here is the velocity will also be perpendicular to that loop. The magnetic field is still in this direction, so when we do the force, when we try to find the direction of the force, it turns out that the force will just push the charges towards the top of this, but they're not going to influence these charges that are moving through there. So they'll just go to the top of the conductor here. All right, so since we have positive charges being pushed up and down over here, then an electric current will start going through the loop. So remember that whenever we have a loop moving in a magnetic field, then we have to think about the motional EMF. So motional EMF is equal to the magnetic field times the length of the object that's moving times the velocity. So here we have a combination of two different lengths. So we have this length and that length of the wire, of the loop, that are moving in the magnetic field. So there's going to be contribution in the EMF from both of these L's. So here I have the EMF is B times 2L times V sine theta. So usually there is not just a single turn of wire here. There are n turns of wire. So the wire would come up and then go around a few times and then back out this way. So to account for the contribution of all those n turns, then the EMF will be n times B times 2L V sine theta. So we know that the loop is rotating with an angular velocity. So we can say that the velocity is angular velocity times r, omega r. Now this, the r is actually half the width of the loop. So that means that the velocity is omega times w over 2. Also, we know that the theta in the sine theta is angular frequency times time. So then when we put everything together, we end up with the EMF, which was number of turns times magnetic field times twice the length times the velocity sine theta, is now number of turns, magnetic field, twice the length, and for velocity we have angular velocity times the radius, which is width divided by 2, sine instead of theta we have omega t. So now we can cancel out the 2's, and the L times W, that's L times W, will give us the area of that loop. So the EMF then will be NBA omega sine omega t. That means that we can set this quantity as the maximum EMF that this loop creates and call it epsilon naught. So then the EMF is epsilon naught sine omega t. So we have something that looks like this. There is an EMF, a voltage that is produced by this loop that is moving in the magnetic field, and it fluctuates between some maximum EMF and minimum EMF, and that is given by the number of turns. So the more turns, the more EMF, magnetic field, area, and omega. So one thing to pay attention to, so we saw that this is an alternating current, but that happens if we look at the direction of the currents when the loop is turning. So if the loop turns in this direction all the time, this part experiences a current going up while it's oriented like this in the magnetic field. But then when it makes half a revolution, when it gets to this point, the current through this portion will go down. And then it makes another half a revolution and the current goes up. So the current goes up and down every half a turn through each of these portions of the loop, which means that the current alternates direction as it's rotating through the magnetic field. So here we have the loop again, and I cleaned it up a little bit. So we know that there was a current in the loop because the loop is rotating with this velocity. So now, since there is a current in these portions of the loop, we can now apply the magnetic force is equal to the current times the length of the wire b sine theta. And when we do the right-hand rule, we notice that when we place our hand in the direction of the current, bend our fingers in the direction of the magnetic field, our thumb is going to stick out this way. If we place our hand in this direction, bend our fingers in that direction, our thumb is going to stick out that way. So what we're noticing here is that as the loop is rotating in this direction, there is this pair of forces that's retarding that motion. It wants it to go in the opposite direction. So we call that counter torque. So whenever we try to produce current by providing some sort of energy to this loop to turn it, while it's producing current, while it's sending current through these wires here, it's also experiencing this counter torque. So we have to have a good balance of the amount of current that's produced and the retarding force, this counter torque, so that we get a maximum amount of current that is being transferred to the outside world. Now, another thing to note about this particular loop in a magnetic field, we have seen something like this before. So before we talked about an electric motor, and the way an electric motor operated was that it had a current originally going through it, through this coil, and as a result of this current loop being in a magnetic field, it started rotating. So it converted electric energy from the current into mechanical energy. The electric generator operates the opposite way. It has to be rotated mechanically somehow. This loop has to be rotated mechanically. And as a result of the loop being rotated in a magnetic field, it produces an alternating current.